Are you ready?
¡Atención!
¡Oh la la! ¡Oh la la! This DJ is so funky, man.
I was improvising.
Oh yeah.
Oh yeah.
We stand out like bird shit on a black shoe.
Dear Shapes enthusiasts, welcome back to the BUTTMAM Series. You like my intros? You know, I'm just trying to keep it fresh. Anyway, last episode we spoke about how the machine handles tri-floats, and today we'll look at the duo floats. I selected another shape for today which will help with the explanation, so let's have the factory produce that first, and then we can dive right in. There we go. This shape will be our point of departure for today. You can see that in analogy with last video, I made the shape systematic again. So the colors of the colors of red, yellow, green, blue, they refer to the pieces that the quadrants belong to, and the shape forms of circle, square, star, windmill, they point out which layers of the final shape the quadrants belong to, alright? Keep that in mind, because that will be helpful later. So, let's get rid of that, connect this again, the way it was, there we go, and then we're going to zoom out, and we are going to go to our duo float cyclers. You know, we looked at the quad cycler, we looked at the tricycler, we looked at both cross filters, and now the point of departure is going to be here. If I get out of this screen freeze, there we go. And I would like to remind you about the wires we are looking at, because the further we move ahead in our story, the more wires are going to, you know, meet up together, bunch up, and the harder it's going to be to keep the overview, you know, because you only have, you know, the blue wires and the green wires, and you just have a bunch of those lines running parallel. It just gets harder and harder. The further we move along, it gets harder to keep an overview of which values all of these wires contain. So let's recap. Here, I have my final shape. Here, I have a copy of the final shape. These two lines, they output quad float candidates, which in this case we don't have. And these four lines, they output tri-float candidates, which in this case we don't have either. So that means that neither of the cross filters is actually going to cancel anything out. And that means that these four lines that come out of the second cross filter, well, they just contain all of the quadrants of the original shape separated per layer. So this is the top layer with the windmills, this is the second layer from the top with the star shapes, the second layer from the bottom with the rectangles or the squares, and the bottom layer with the circles. Okay, so duo floats. Let's talk about duo floats first. I prepared a little display setup, and we're going to assume that we are going to stack this green shape below this blue shape. Okay, so this will be the result. In this combination, there is a potential total of 8 duo floats imaginable. There's 1, this is 2, this is 3, this is 4, this is 5, this is 6, 7, and 8. Now, a preliminary remark that I would like to make is that if you are still with me on the bigger picture of this machine, then you should be able to answer the question, can all of these shapes be output at once? And the answer is no, they can't. Because in order to be able to output all of these shapes as all of these duo floats as candidates, we would need to have a combined total of 8 quadrants occupied in our shape on 2 layers. And if that is the case, then none of them will be floating layers. And if we have no floating layers, well then, our fast lane module, which we spoke about in video 11, well, that one will catch the shape, and these duo float cyclers right here, well, they won't get any input in the first place. Okay, so this is purely theoretical. A theoretical combination of 4 plus 4, so 8 quadrants, could lead to any combination of one of 8 quad floats, but never all of them at once. I believe there is a maximum of 4 lines that can be output at any given time. However, the amount of stacking combinations is 8, and therefore we will need to run 8 candidates into our cycler module for the duo floats. Now, 8 is an overseeable number. It's not an insanely huge number. So what I just did is I just hard-coded them into the machine. Okay, I just basically brute forced it again. So we get our, let's start right here. We get our top layer, our 4th layer, and the 3rd layer. And I'm just going to cut out all the quadrants, all the possible duo float combinations on those 2 layers for all of the quadrants, and I'm just going to combine them. So one of the lines, in this case the 3rd layer, comes from the bottom, and, I am simply going to stack all of its quadrants with all of the quadrants on the top layer, which in this case come from the right. So I cut it all up, and I just combine all of the possibilities for a total of 8 output wires. Okay, let's have a closer look at one of them that's actually outputting a signal. So I take the top layer, I take the 2nd layer from the top, and I see whether any of the combinations are possible. Now, I would like to refer back to how you can stack floating pieces. By now, I would like to assume that you know this, so you need your scaffolding pieces. And now we're going to get to an interesting thing. I take this layer, I rotate it 180 degrees, and I use that as a scaffolding piece for both layers. Okay? And then I have this very simple 2x3 module that is going to tell me whether I need to rotate my shape prior to cutting, yes or no. Because after all, the output of this is going to be this weird shape of which half is going to contain our actual quadrants, the floating stack that we want, and the other half is going to be scaffolding. We need to throw away the scaffolding, and we want the machine to be able to determine, obviously, which side it has to throw away. So initially, what I do is a trick that I showed you before. I cut the shape into left and right, and I'm going to rotate it 90 degrees once, and the actual piece, it will have an output on both sides, so the AND gate will toggle this transistor, will enable this transistor, and only on the side that contains the actual piece, the signal will be allowed to continue. But we have an additional problem, and that problem is, as always, that the cutter in this game always cuts vertically, regardless of its orientation. So it will always cut the left half and the right half. And that may not always be what we want. Okay, let's zoom out and let's get to another display setup right here. So there is a total of 8 duo float possibilities. Come on out. There we go. This is the first one. This is the second one, the third one, and the fourth one. And we have a mirrored set, so we get 5, 6, 7, 8. These are the possibilities for a duo float. Now, the question is, how are we going to let our machine determine which side is the scaffolding and which side is the actual piece? And also, since the cutter always cuts vertically, we also need our machine to be able to determine whether it needs to rotate the shape 90 degrees prior to cutting, yes or no, and then optionally rotate it back afterwards. How are we going to do that? Well, I showed you the module before. It's super basic. It's 2x3, so 6 cells. It occupies 6 cells, but the logic that goes into it it reaches quite far. So I want to take you on that journey. All right? How did I do that? Well, look at these shapes. I have color-coded them, so you see that the actual shape contains colored squares and the scaffolding contains uncolored circles, okay? Now, a very important part is that my scaffolding on the top layer is diagonal and on the bottom layer is lateral. So let's take the top layer off. If we take the top layer off of these shapes, this is what we get, okay? These are the bottom layers of all of these shapes, respectively. And now let's have a look at this. Because of the way I colored these shapes, we can tell just visually whether we need to rotate these shapes if the cutter works vertically, yes or no. So let's have a look at the first one. Do we need to rotate this? Well, if we cut it left and right, we get an actual piece together with scaffolding. So the answer is yes, we would need to rotate this first. Now let's have a look at the second one. It has its pieces on the right, the scaffolding on the left, which means we can cut and we do not need to rotate. The third one, we have our pieces on the bottom, the scaffolding on the top. So cutting left-right would create a mix that we don't want. So again, we want to rotate this. And this one, it already has its pieces oriented the way we want, so we can cut vertically. So we don't need to rotate that. And the same thing goes for the left half. Sorry, for the other half. So we can see that if we have our actual quadrants either right or left, then we don't need to rotate. And if we have them top or bottom, then we do need to rotate. Now, how are we going to build this logic in my machine? Or how have I built this logic into my machine? Well, I worked with analyzers. And I hope that you remember that the analyzer, when it analyzes a wiring signal, it will check the top right half of the shape, the top right corner of the shape. If there is a quadrant there, it will have an output. And if there is no quadrant there, it will not have an output. Okay, keep this in mind. Let's look at something else. Let's go here. So let's look at this first scenario. In this first scenario, will we have to rotate the shape? Well, the answer is my actual quadrants are on top, and therefore, yes, we will need to rotate. Now, if we take off the top layer and we run it into an analyzer, then the analyzer will have an output because there is a quadrant in the top right corner. Okay? If we rotate this shape 90 degrees clockwise, the analyzer will not have an output because we do not have a quadrant in the top right corner. Keep this in mind. Let's go to the next one. Let's look at this shape. Will we need to rotate this shape prior to cutting? It has its quadrants on the right, and therefore the answer is no. We won't need to be cutting. Let's look at this shape with the top layer taken off. If we look at this shape, it has no quadrant in the top right corner, and therefore if we run that into an analyzer, there will be no output. If we rotate the shape 90 degrees, there will still be no output, again, because there is no quadrant in the top right. And now we can start making small additions in our heads. If the analyzer of this shape is a 1, and the analyzer of the same shape that is rotated 90 degrees is a 0, we want the shape to be rotated. So in other words, I want 1 and 0 to equal 1, if you are with me. In the second scenario, I want 0 and 0 to produce a 0, no rotation. Let's have a look at the third scenario, this one. Will we need to rotate the shape? Well, the quadrants are at the bottom, therefore, yes. If we analyze the shape, this one will not produce an output for the analyzer, and the rotated form will produce an output for the analyzer, and therefore 0 and 1 should produce a 1. And the fourth scenario, in this case left, we won't need to cut, and if we analyze the shapes, then we will get an output from the analyzer, and in its rotated form we will also get an output from the analyzer, and therefore 1 plus 1 equals 0, 0 plus 1 equals 1, 0 plus 0 equals 0, and 1 plus 0 equals 1. And if that means anything in your Shapes.io playing mind, well, then that should be shouting out a XOR filter to you, an XOR gate. That should be the conclusion that you reach from that, because after all, an XOR gate, if you combine a 1 with a 0, then the output will be 1. If you combine a 1 and a 1, the output will be 0. If you combine a 0 and a 1, the output will be 1. And if we combine two zeros, then the output will be 0. And that is exactly the behavior that we want. So now let's get back to the super simple module that is the 2x3 analyzer. What I do is I run the bottom of both layers into an analyzer module. I rotate it 90 degrees and I run it into another analyzer module. The output of that will determine whether we have to rotate our shape prior to cutting, yes or no. And in this case, well, if the output is a 0, then thanks to this NOT gate, it means the shape is not rotated, it does not have to be rotated, and in the other case, it will have to be rotated. And now, after performing, so this mechanism will ensure that we always get our actual piece versus our scaffolding output either left or right, but never, never skewed. And then the only thing we need to take into consideration is if we rotated our shape beforehand, before cutting, well, then we're going to have to counter rotate it after cutting again. So I run this signal on. I pull this signal to the end here, and it's going to do the exact same thing. It's going to block one of the lines, and it's going to allow another part of the lines the rotated one to pass, or vice versa. And that is how we get a potential total of 8 output lines right here, but only a maximum of 4 of them can contain actual values. That's how that works. The rest of it is very similar to what we've seen before. So, with the quad floats, we only needed 1 module. For the tri-floats, we needed 2 modules, because tri-floats can be either a combination of either layers 1, 2, and 3, or layers 2, 3, and 4. Well, for the duo floats, we need 3 of these modules. This is going to check combinations of layers 3 and 4. This is going to check duo float combinations of layers 2 and 3. And this is going to check for combinations of duo floats on layers 1 and 2. So, apart from that, the behavior we see here is very similar. The candidates that have come out of the duo float finder module, they are fed upwards, and they are going to run into a cycler module that we have seen in plenty of videos before. In this case, we see that we have 1 candidate, and it has also been selected in our final solution. We run a very similar filtering mechanism into our twin cycler, which I'm not going to talk about because the twin cycling mechanism is identical to the tri-floats and the quad floats, right? So that's what that does. We have the exact same thing again, where the signal coming from the cycler is going to match one of these, which is going to determine which signal is allowed to continue. And that signal will be the selected candidate to continue onwards into the rest of the machine. Now, we have another filter mechanism right here, because remember that I do whatever is in my power to reduce the amount of piece combinations that my machine is going to have to try as much as possible. I want to limit that number, I want to bring that down as much as I can. So, the machine on the left checks for layers 3 and 4. The machine on the right checks for layers 2 and 3. And this means that we may have overlap on layer 3, correct? So, depending on the candidate that we have selected here, I'm going to run a filter that is going to cancel out all of the incompatible shapes with overlap. And that is what these filters do. So, let's have a look at this shape. Remember the sequence I talked about? In this shape, we have a windmill quadrant and a star quadrant. And because the star quadrants are always on the 3rd layer, that means that the star quadrant is something we are going to look for overlap. So let's see if that happens, okay? Let's look at the second module and see which candidates it produces. And we're going to see whether any of them has a blue star quadrant on it, because if it does, then that means it's an incompatible piece. Let's have a look. Is the first candidate no overlap, no output. Second candidate, no overlap, no output. But third candidate, overlap, because it has a blue star quadrant in it. Well, what do you know? Because of the filter modules, that signal is blocked, and this signal doesn't get to move onwards into the cycler. So this cycler has only 2 candidates to consider, which is this one and this one. An exact same thing happens right here, right? This is an exact replica of this right here, with the only difference being that this applies to layers 1 and 2, this applies to layers 2 and 3, and the overlap that we may get will be on layer 2. So let's have a look. Layer 2 has rectangles on it, so in this case it's the bottom left quadrant that's on our second layer. And we're going to see whether any of the shapes we find have a yellow quadrant, a yellow square in the bottom left. Let's have a look. Well, this machine has only one candidate, and there is no overlap, and therefore the signal is allowed to continue onward to the cycler. That's how that works. Now, when we're done with that, we are going to let the signals run into the final cross filter. And there is something else I want to point out at this time. Even though the system is completely, the logic behind what we are doing is completely the same as what we have done so far, the situation is getting more confusing because of the accumulation of wires that we are getting, because the quad floats are coming in, the tri-floats are coming in, or the wires that may carry the signals, they are coming in. And once again, because you only have two colors of wires, you need to pay very close attention to which signals can be carried by which wires. Okay, so let's have a look at what's going on. We have our 4 actual shape layers right here. Okay, I have a frame drop again. There we go. We won't be needing the top layer anymore, so that moves up and it continues. Now, these are the bottom 3 layers of our actual shape, and they are joined by the 2 potential candidates of our first duo float counter. So that's these top wires right here. So now we have a group of 5, 3 actual layers with 2 duo float candidates. Let's follow these lines along. Now here is where the 3rd layer moves up and doesn't continue because we won't be needing it anymore from this point forward. And we have another 2 duo floats joining this group. These with the first duo floats on layers 3 and 4. They move down. It's these 2 lines right here. So now we have duo floats on layers 3 and 4, the actual layers 1 and 2, and the duo float candidates of layers 2 and 3. You're still with me? I told you this is confusing, right? So you have to keep a really clear mind of what you are actually doing. So, and at the end of this, we are going to get we're going to be joined by the candidates that come from the layer 1+2 duo float checker. And now the lines are automatically organized, so layers 3 and 4, layers 2 and 3, layers 1 and 2. And they are going to run into the cross filter module. Now again, I may have exaggerated a little bit with the cross filter module because I believe these units right here are superfluous. But the thing is, I confused myself so much with this TMAM that at a given point, whenever it did what I wanted to, I was like, oh, it works now, don't touch. So I'm more than willing to admit that there are definitely some redundant, units, logic loops or whatever, redundant modules in this machine. I have no problem in admitting that. And I believe now that I look at it, well, I won't be needing these 2. So what I'm going to do is I'm going to take the final shape once again. Here it goes. And I'm going to deduct from that the quadrants I may have found in the quad float checkers, these 2, the tri-float checkers. Come on, screen freeze again. There we go. Tri-float, and now finally the duo floats are added to that, and the result of that will be the remainder. That will be the remainder of all of the pieces of our shape, all of the quadrants of our shape that are not contained within any of the other floating pieces that we are currently considering. All right, so these wires, they contain the remainder. And as you can see, in this case, we only have one actual quadrant that pertains to that group. So all of these wires meet, and they are going to continue into this module, which is, I call it the lane nester. We are going to have a look at that in the following video. So we have reached the end of this video. I hope you didn't get too confused. I hope you are still with me. I hope you are, seeing the big picture. It is slowly coming together how this machine works. Not only when you look at it from a global point of view, but also now that we are really digging in deep and looking at all of the individual units. I hope you still see, or you're starting to get a clear picture of how this machine actually works. And having said that, once again, I want to thank you very much for watching. I hope you had fun, and I hope to see you again in part 15, where we will be talking about the TriFloat Nester module. Thanks again. Have a great day. My name was Bins. Take care. Bye-bye.